Welcome to a lesson with Dr. Powell. Let's take a look at symmetric matrices and an explanation why they are always diagonalizable. Okay, now let's suppose that we have the matrix A and it's symmetric, and we raise it to an even power. Well, we can actually think of that if we we can split it up into a sub n and a sub n again. Now notice that since A is symmetric, if we take the transpose of A sub n, that's the same thing as A sub n. So this guy right here, A sub nt times A n is really A to the 2n. Then if we have a vector on this side, we put the transpose of the vector over here. Notice what this is over here. This is simply the transpose of this. And this is a vector, and this is a column vector. This is a row vector, and it's the same one, just written as a row. So when you make this matrix product, it's really a dot product between two things. And this dot product is equal to 0, which is this statement. Now this 0 over here means the 0 vector. So maybe we'll notate that. A, right? And we're thinking of A as being a square matrix here. Okay. So we'll just kind of remember that when I write 0 here loosely, that just means a 0 vector. Now this is only true if the vector itself is 0. I mean, remember what a dot product is. In some sense, it's the square of the length of a vector, and that would only be true if it was 0 anyway. So the dot product right here is equal to 0 if and only if the vector we started with was 0. So what does that mean? That means that if a to the 2n v is 0, that means that a to the n v is 0. Let's look at that in a situation. What if we knew that a cubed v was equal to 0? 3 is odd, right? Well then, of course, if you put another a on, you would get 0 again. A to the 4th v would be 0. Well, that implies that a squared v is 0. Hey, if you know that's true, using the same argument, you know av is equal to 0. Wait a minute. In general, if you have a to the n to any power at all, so a to any power, and you put v right there, and that's equal to 0, and you know that a is symmetric, that actually implies that av is equal to 0. This is useful when we're thinking about diagonalizability, because what if our matrix represented as x is symmetric? That means, for instance, a linear factor, an example like x minus 1 would be symmetric. Now, because you take a symmetric matrix and you subtract something down the diagonal, that's still symmetric. All right, now what if we had x minus 1 cubed v is equal to 0? Well, that will imply that x minus 1 v is equal to 0. This basic idea means that the minimal polynomial for a symmetric matrix has no powers larger than 1. So because this isn't minimal, you can go down to 1 every time. So this actually means that we can get enough eigenvectors, because we need to have the right number of them to fill out a matrix, the matrix P that we're using in the diagonalization process. We need to have the right number so we can write them as columns and get a matrix, so we can invert over here and get this working to get our diagonal matrix over here. So we can get enough if the minimal polynomial has no powers greater than 1. So, and so we can know that we can actually go ahead and diagonalize the matrix if it's symmetric. That's a property of symmetric matrices, where the transpose is equal to the matrix itself. Okay, so here's a little example. All right, we can, if we look at the, so we get this matrix right here, we can compute its characteristic polynomial, think x minus So exit down the diagonal minus the whole matrix. Take the determinant. We can use a cofactor expansion. X minus 3, so x minus 3 times the determinant of that guy, and 1 times the determinant of that kitty corner guy right there. And we don't need to change the signs in these because it's plus minus plus. So computing this, we end up getting this, which is nice. Okay, so we have, we know what our eigenvalues are, 3, 4, and 2. And for each one of these, we can, we're going to use kernels to find the eigenspaces, just because there's more than 2 factors. There's 3 factors here. So taking a look at that, we compute x minus 3 and we take a look at its kernel just by putting it in reduced row echelon form and using our little technique to get the basis quick. So reduced row echelon form, we look at the non-pivot columns, and we have this technique where we look at for each pivot, if it is in the same row as a non-zero entry in a non-pivot column, which column did this come from? This came from column 1, so that means it's going to keep this guy in row 1, but it's going to change its sign. And then after that, you just put 1s down the diagonal and you put an extra 1 there. We use that basic kind of trick to just quickly go from here to reduced row echelon form to the basis. Or you could just find out all the solutions that would make this give you zeros over here and find out a basis for that. So however you wish to do that. But anyways, we get the eigenspaces, and we could just take our bases for them. We could just take these basis vectors themselves, and then we can write this out. Okay, so we have for each basis vector, so this one corresponding to eigenvalue 3, that one to 4, that one to 2, and we have just diagonalized this matrix A. We take this guy, take its inverse, and we end up getting this. Now here's an application of diagonalization. One little thing that we can do with it. So this works particularly for symmetric matrices, but we'll throw this in right here. If you have, if you want to raise the matrix A to a power, it's kind of nice because using the diagonalization, you get a lot of cancellations, and it ends up just being your matrix P times D to the N times P to the minus 1. So you're really just raising, you reduce the problem to just raising a diagonal matrix to the nth power. Now, how do you raise this matrix to the nth power? It actually is as simple as doing the following. Done. So this enables us to have a nice simple formula, actually, for a to the nth power. Very, very straightforward, very simple, simplistic. And that's one application of diagonalization. Enabled to diagonalize a matrix, and we can always diagonalize a symmetric matrix. Thanks for watching.